The RSA theorem is the justification for the RSA process. Informally, it says that if somebody uses Bob's public key to encrypt a private number for Bob, and remember a private number is just the translation of a private message, and if Bob then uses his private key to decrypt the encrypted number, he will end up with the original message, or more precisely, the original private number. So let's now make a precise formulation of the theorem. Down the left-hand column here, I've recalled the toy RSA example to motivate what we're doing. And here's the precise statement of the theorem, which is essentially what we have already been doing. So we take two primes, P and Q, which are distinct from one another. We let n be the product of the two primes, and m be the product of P minus 1 times Q minus 1. We suppose we have, well, first of all, a number e bigger than or equal to 1 and less than m, which has no common factors with m. So the greatest common divisor of e and m is equal to 1. We've normally been taking e to be a prime and assuming that e does not divide m, but that's equivalent to this in that case. So this is slightly more general. We don't really need that e is a prime. Because the greatest common divisor of e and m is 1, then we know by a previous theorem, the multiplicative inverses theorem, that there must be a d which when multiplied by e gives us 1 modulo m, and d will also lie between 1 and m. So these are our assumptions, that e and d lie between 1 and m, strictly less than m, bigger than or equal to 1, that the greatest common divisor of e and m is 1, and that de is equal to 1 mod m. In other words, d is the multiplicative inverse of e. And now, suppose that we have w, that w is the private number, and then it was encrypted by Alice by taking w to the power e. And remember that n and e were the public key, so Alice takes her private message, a private number, raises the power e mod n, and that gives C the encrypted number, which is published. Then Bob raises C to the power D, and D was his private key, modulo n, giving us another number, capital D, in the range from 0 to n. The theorem is that D, the number that Bob obtains by decrypting the encrypted C, is indeed the original private number W. So the claim is that D is equal to W, and that's the same as saying that W to the E to the power D is equal to W mod n, because D is just C to the D, and then I've replaced C by W to the E. And that's all allowable because we're working modulo n, and if I replace C by another number to which its equivalent modulo n, which in this case is W to the E, then I get W to the E to the power D, modulo n will be the same as W. So basically all we've done here is we've just replaced D by C to the D and C by W to the E. So we want to show, in effect, that if I take any number W in the range 0 to n, if I raise it to the power E and then raise it to the power D, I'll end up again with W if I work modulo n. So that's the statement of the theorem. And let's have a look at the toy RSA example. In the example here, W, the private number, was 15. Alice encrypted it and obtained 9. And then Bob decrypted it and obtained 15, which, of course, by our theorem, is the original number W. So you might have checked this and other W from the table. So for example, if we take the number we've already looked at, if I take W is equal to 15, and if I raise it to the power 3 modulo 33, then I obtain the number 9. So this will be the encrypted number. Then, that's here, decrypting it, we raise it to the power 7, modulo 33, and so we obtain 15, which is the same as the original number. Let's do just one more example. If I take the number, say, 24, and then, as does Alice, encrypt it, in other words, raise it to the power 3, modulo 33, that will give 30. If one then takes 30 and decrypts it, in other words, raised to the power 7, one gets 24, which is the original number. So you might like to do a few examples yourself.